running Mac OS machines. Mac OS runs on x86.
But would it?
The
What would it be useful?
Also,
I could think of some really disgusting.
I bet you just couldn't validate one.
You can.
Are we live?
and then once you update it, it'll turn the Bluetooth back on, even if I don't want it on.
That's because they're watching you.
There's a bunch. I could think of a number of really disgusting things you could do, because like you can set up like macOS just default allow all incoming screen sharing connections.
I don't know if any of the red team know how to do it.
Can someone check if we're live?
Yeah.
The point is like,
Yeah, I sent the link
So
in
you should
chat.
ask that at the comp.
Because once I get
'Cause
confirmation.
I would know. You're going to you bring macOS in because it specifically notes that you're not supposed to run it unless you have a license, and the license is lost from your current.
It says live.
Oh, is it?
So you are breaking the EULA.
I might need to do something.
Well, yeah.
I swear, we need to bring that up.
Yeah, that isn't. If they're going to keep expanding it to the internationally, that's an important one to bring up because it's probably not going to be that long before you end up sent down with a European Union citizen. And now you have to follow GDPR.
Why isn't it? Ah, are we good now?
What are they going to do? Take the $3 ICH has?
We can cut all this out later. That's fine.
$8 for me. Citizens weren't draft on that.
You can also just and then post it later.
Okay, cool. Well, we'll hope this is working. Either way, it's getting sent to YouTube server.
But, oh wait, it's up now.
Oh,
It's
good,
just
good,
really
good, good.
delayed.
So we have a pretty high delay, but that's going to be fine. I figured I was going to start off with a little bit of news. So today is a very special day. It is the Leap Day, and that means everyone in software development who forgot about it the last couple of years is getting pwned. So right now it seems like New Zealand is one of the biggest targets. You're not allowed to pump gas in the self-service stations right now. A little bit of a problem. And then also PlayStation is having a little bit of trouble. Everyone who wants to get on the EA servers has to change their clock because February 29th apparently doesn't exist. And another one, we have another Windows kernel flaw. It is a 0-day released by the infamous North Korean hackers Lazarus. It does require administrator privileges, so this is going to be more useful for your persistence, trying to get a nice kernel level backdoor inside. And then once you do, you can check this out. Now that we have the news out of the way, let's get to presenting. So, this is a nice introduction following our previous reverse engineering presentation, and it's going to be covering something called stack smashing. So first off, let's talk about when this was actually used. Not very often. You're going to find that binary exploits are very, very, very few and far between. But this is an example of something that happened back in the 90s with something called the Morris worm. It essentially was meant to just kind of go across different systems and then show how vulnerable everyone was. But there's a little bug in the code with it trying to check if it already existed, where it ended up taking down a lot of government websites and causing hundreds of thousands of dollars worth of damage from an MIT student. So always got to double check your code. But essentially, this is the classic buffer overflow with a little bit of a twist to try and spawn a shell. If any of you recognize it, you might see at the very bottom a little thing called bin, a little thing called sh, trying to get a shell in there. And then you can also see the buffer in the upper right-hand corner. And we're going to kind of cover what all of that means, and then we'll come back to this with your newfound knowledge. Starting off, what is a stack? Why are we smashing it? So each process, which is something that's basically running on your computer, has its own little virtual memory, and this virtual memory has a specific structure. You can see at the very top, there's something called the stack, and it's where you put all of your temporary variables. When you're creating your I for a for loop or anything like that, it'll just get thrown on the stack. So that way you have a nice bit of range and a nice bit of flexibility for whatever you're trying to make. Below that is the heap, which is going to be a little bit more static. but it is for all of your pointers, all of your larger bits of data. So you can see the difference between the character pointer variable versus the character variable array is that the pointer is going to be just this memory address that's stored on the stack that points to the heap, whereas the variable array is going to be all of the data actually stored on the stack. And that's a very important distinction because yes, you can also do heap smashing, but we're going to be focused on stack smashing today. So past that, you also just have the basic static data, all of your code somewhere else, and you kind of see the text in the code is near the bottom, and that is going to be useful for later when we're trying to jump around in it using stuff that we have in the stack. So, trying to actually smash the stack, it is important to look at what's stored there. Each time you call a new function, you store the previous function's variables, registers, and then you also store something called the return address. It points to the next instruction that would have executed after you return back, and then that's stored at the very bottom. And after you kind of complete your execution, you clear out all of your registers, you return back, it goes to that address, and then it puts everything back in the registers that you need to keep going with your execution after you do like a printf or an fgets or whatever you're trying to do calling a function. So what can go wrong? When you are writing things to the stack, it is the programmer's job to make sure that it is the right thing in the right place in the right amount. If the programmer doesn't do that, then there's some kind of funky stuff that can happen. And if you put data in, you're going to start going into the previous, what is called the stack frame with all of the return address and the previous variables that were used. And then you're going to start changing what the function that you return to starts doing. So if you kind of see this basic example, we have the frame information with just a normal input. You see at the very top for this second picture, we have a bunch of 41s, which just means that I put a bunch of A's in there. And then you have various other data on the stack. And most importantly, if you look at this top picture, you can see something called saved RIP equals this value. So RIP stands for return instruction pointer, and that is the point in memory that it is going to try and return to. Or, okay, it is a x86, it's a little bit weird. This is a value that points to an address, and we actually have a pointer to that pointer to make sure we're getting to the right spot. So this is the piece of memory that holds the pointer to the actual address that we're going to return to, but this is the value that is stored on the stack. And if you look down here, you can see this exact same value a little bit further down from where our input is. And if you kind of do a little bit of calculation, you can see that this is 8 bytes. These are 8-byte blocks. So this value right here starts at the DDA0, and then right over here we go to the DDA8, and that'll be important once we actually try and break some things. So let's say you didn't actually check if the user's inputting the right amount of data, and they go a little bit too ham with their A's. We get this. First of all, it breaks the parsing. It doesn't know what the block size is anymore, but we have a lot more A's, and you can see that our return instruction pointer is just kind of a bunch of 41s. Sadly enough, that doesn't point to anywhere in the program, so that's just going to cause a big problem for us. But if we look at this, we can even point that out in the memory here, where we can see this DDA8, and we have a bunch of 41s, and then as with everything in C, the string ends with a null byte, which is just 0x00, and then we can even see the very last bit of information from the original instruction pointer. If we see right here, it's a 7F. And of course, as we talked about in our reverse engineering, there's a little something called endianness, where A8 is technically right here, and that's that first byte, and then the next byte is here, it's the C2, next one's DE, and then F7, FF, and then 7F, and so on. So this actually isn't the right order that it's stored in memory, And it gets even more confusing because these blocks are in the right order. So it does go this block, then this block, then this block, then this block, then this block, but the bytes are backwards in each block, which you also may recognize from the Code Breakers challenge, where I got tripped up by that trying to read keys, where you had a little endian portion here, and then each portion was kind of going one after the next. So now that we can see we have overwritten our return address, or our return pointer, we get a nice little seg fault. And there are a couple different uses for that. One, if you're in a sandbox environment, it might take data, and then if you can get a seg fault, it'll just crash and pop you into the original shell. So if you're running a sandbox as root, and someone manages to get a seg fault, you can just have an immediate root shell. Yes?
So what's the difference between the return instruction pointer on the left and the saved return instruction pointer on the right? But before the second was overwritten.
Yeah. I believe the original RIP is the one for, it would be the current function, and then the saved one is the one that you're going to go back to with an RIP. So if you were to call something right now, it would put that RIP into the stack. Whereas if you were to turn right now, it would go to where the saved RIP is pointing. So it's just different levels there. Yes. And then you can also see where the stack pointer is pointing with this stack frame at. Just a little bit of useful information. And you can also see some of the GDB commands if you want to see some of this stuff yourself. I stands for info, F stands for frame, so you can get information about the stack frame. And then also X is for examine / the amount, the type, and then what you're examining. So you're examining 20 hex values at the stack pointer, which the $ just means a register. So just a little bit of useful GDB info if you're trying to do some of this stuff yourself during a CTF challenge or whatever. And once we've actually smashed the stack, there are a couple things we can do with it. So one, as you saw with this 414141, we could kind of put whatever data we wanted in there. So we could have replaced this with the memory address of, I don't know, a function that starts a shell for us, or a function that prints out what password the user is currently using, or a function that calls home, or anything like that in the code. There's a bunch of different things you can use, and because the return address kind of just goes like, oh, this is where I'm supposed to go, it'll just go there and not ask any questions. And you can even see, if you format it properly, you're just going to have the address here, 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 here. And then you'll get the null byte terminator right there, right where it should be, right where the memory address likes it. And if you have something called a ROP gadget, you can do some more interesting things. So ROP stands for Return-Oriented Programming. And that is for all of the functional programmers who like writing these little utility functions that will do something simple and then just go back to the main function. So instead, we can just have our function do something simple and then return. So if you look right here, and if you've taken 381, this might be a little bit more familiar. If you haven't, this is going to be a little bit more confusing, but essentially we are taking a pointer to this value and moving it into this register and then returning. That's all it's doing. So we can kind of chain these together and get our own little program running, because each time it returns, it's just going to go to the next value in the stack. So every address that you put consequently, it'll just keep on going and going and going and going and doing different things. So that is the kind of like ROP/JOP. And of course, ROP is return-oriented programming using these RETs. And then JOP is jump-oriented programming, which is like all of your for loops and if statements kind of jumping everywhere. You can also make it jump to somewhere that you want to. And then some mitigations that will be covered a little bit later. We can either write better code. You know, sometimes you just actually need to double check what the variable size is when you're getting data. You can use libraries because, I mean, most people have actually done the work for you and they did it correctly and it's been double checked by multiple people and hackers have already tried to break into it. And then Canaries are a little thing to make sure no one's actually trying to thrash the stack. ASLR makes sure that everything is random. And then pi makes sure that everything is random in the instructions. But as said, that will be covered a little bit later. Does anyone have questions about possible things you could do or want to learn anything more about this? I know it was a little bit short. I guess not. Let's see. Anyone have any questions about malware in general? How to reverse engineer different programs? I am willing to do a little Q&A session about reverse engineering, binary exploitation, anything like that. Yes?
Maybe I missed it, but for example, in that note there, it shows how you have the that payload at the bottom.
Mm-hmm.
How would you know where to set that return that saved RIP to make sure you get into that payload?
Oh, yes, you can do that with regular static reverse engineering. You can check what the address is, or you could also pop it into GDB, check what it actually sets it to. Either way, you can see what that saved RIP is, and then you can even look at the function it tries to go to. The one it gives in our examples here, this is through libc, just kind of jumping into main. That's why it's so far off. Normally this will actually be closer to where you're executing code, a little bit lower, whereas you can see this is kind of up in the stack area. But yeah, that's how you can double check where the saved RIP is, and the current RIP is also available through GDB and stuff like that.
Does it become much harder if something like ASLR is on?
Yes, it does. It gets quite harder because if you don't know where the saved RIP is, or if it's changing constantly, it makes it really hard to make a consistent payload without popping it into GDB and trying to search for it and then input it manually, instead of just having a Python function that pipes everything into the function that you want. There are ways to turn ASLR off if you want to use this as a persistence method. It is a variable that is going to be in your, I believe, the kernel level. Yeah, it's going to be kernel level to see if your programs are being put in random locations. So it's hard to do, but you can turn off ASLR, and I would never recommend to turn off ASLR on your machine. When you're doing this, if you want to make one of these challenges yourself, if you want to get into this, there is actually a flag that you can do in GCC. I would need to look up what it is, but it will automatically make your program static in case you do have weird memory things going on in your C program, but that can also be used for these types of challenges. And if we kind of learned anything today, we can understand this a little bit better. We see right here, we're taking this buff variable and we're replacing all 536 bytes with null bytes to make sure that there's no weird, funky data in there. And then we put the initial 4 bytes to 1, whereas I normally use A's just because it's easy when trying to input the text yourself. And then afterwards, we have another 28 bytes. So because we didn't clear out this I, we're starting at 400, and then we're going to each subsequent value. And then we can also see here where this J is, we're going to be grabbing the jth byte for whatever this string is, and we're going to be putting that into the buffer. So once we do that, we have this little socket to something called fingered, or fingered if you prefer, and that will send all of the data from the buffer into that. And fingered just had this little gets function that was not parameterized quite right, and that's what this attacker used to try and hack it. And if you want the source code, I also have it in my slide notes. And someone did a really nice job doing these cool comments and showing all of the source code for this worm. It's just a pretty old thing, and you can find more malware like this on a couple of different sites. The sites I would recommend if you want to look more into live samples would be VX Underground. They have a large variety of samples. Every single attack you've heard of, they probably have a sample of it, between these advanced persistent threats, archives, different papers. If you don't want to actually get some malicious code on your system, understandably, you can just kind of look at the papers. So for like Linux, if we want to look at some persistence, we have a nice little paper on systemd user level persistence if you want to do something like that when you're making your own malware. Let's see, other than that,
You want to download some malware?
yeah, sure, let's download some malware.
I've got one more question.
Okay, yes.
How do we know how far to overflow or what sections we controlling? Are there any tools to help with that?
Yes, so there is essentially, if you get the source code, you can look at how many bytes an array is and then how many bytes you're getting. But you can also use Ghidra, and you can look at how many bytes are allocated to a variable and then how many bytes you're getting. I don't have any examples with me right here.
Do you know the name of it? There's a thing that like it'll generate a pattern.
Oh, yeah, so GDB pattern is this really nice little command that you can run, and it'll put a pattern of characters like this. So if you saw in the slides, we had complete access to what the RIP got set to. So then all we have to do is check what values in this pattern it got set to. We can search for it, and then we know exactly where to set the memory address if we want to jump somewhere specific. Yeah, and then you can also see if you want to run your own exploit. This is usually the way to do it through this Python C thing. It makes it super easy. You can just do it in GDB yourself. And other than that, yeah, it's really simple. And of course, this isn't really that relevant anymore. Most people are doing pretty good with not letting buffer overflow in. Usually the worst you can do with this nowadays is DOSing a system. If you happen to get in buffer overflow, kill whatever, and then they have to restart it, or they lose some data or whatever. But there's nothing too crazy you can do with it nowadays unless you're looking at some older embedded systems. Let's see. Yeah. Other than that, any more questions? Yes, William.
Where would you, if you're looking to improve at like reverse engineering and such, do you have any good resources, things to check out, exercises, things like that?
Yes, there are loads of exercises between CTFs and a good variety of things. I mean, I have a couple challenges myself at, yeah, we'll see if this ends up being okay. jamesautoj.github.io. I have my reversing challenges. So if you want to look into that, I have the source code, and I also have Docker containers for this Rev 3 and Rev 4, which have a lot to do with what we were covering today. But yeah, and you can even see inside of Rev 3, if we look at the source, we have a buffer size and a flag size, and this is all based on how the challenge actually works to detect if you've done it properly. But essentially, we have a character array. You can see it's not a character pointer, but an actual character array that's stored on the stack of the size buffer size. And we ask someone to enter their password. And once they do, we just kind of get any of the bytes that they answer completely unrestricted. And we put that into nothing, and we just, yeah, does it print it out? Oh, okay, yeah. So it just scans the buffer, it makes sure that it's a string, nothing too weird. That's what that formatting thing is. And once we put all the data in there, if it has overflowed, we're going to get something called a segment fault, which is essentially the operating system going like, you weren't supposed to access that memory. What are you doing here? And that usually happens when you actually try and return. This doesn't get triggered when you initially overflow because everything's okay. But once you actually try to return to hex 41, 41, 41, 41, 41, 41, 41, it's like, what are you doing here? There's nothing here. There's no code here. Why are you here? And it sends a segment fault. And then that gets caught here, and that's how the challenge actually works. But if you just try and do whatever, you can see that if you just put password, you'll get correct password or incorrect password. So it's just normal code. It just happens to be vulnerable to putting whatever data in that you want. Let's see.
And how do you spell the GitHub?
Oh, yeah. So it is, I'm also on GitHub at JamesAutoJ. That's kind of just my professional name there. And you should see it, this spooky 2023 reverse. And I'm planning on making more because reverse engineering isn't just about C code. It has to deal with PowerShell. It has to deal with JavaScript, all that kind of stuff. So next year for spooky challenges, for anyone that wants to compete, for anyone that wants to try things, I will be trying to make a couple of more PowerShell programs that you probably will have to get on Linux because Windows Defender likes to delete anything PowerShell that looks slightly suspicious. But yeah. And I can also throw this in our Discord for anyone that just wants a link to that. And I'll do that once this meeting is over. Can I pull up? I'm going to try and get some PowerShell code then.
I sent a link to your website in Discord.
Okay, sweet. I want to see if I can find a good example of this somewhere. Yeah, so pretty much every single PowerShell malware is going to have this in it. This system.txt encoding, Unicode get string, blah, blah, blah. Here is 64. Here is some 64, base 64 encoded PowerShell. Just decode it and run it, and don't worry about it. So you'll get this base 64 string, and then it'll just run it magically. Windows has gotten pretty good at going, hey, you just decoded something from base 64. Can we double check what that is before we run it? And then deleting the program ASAP, which makes it really, really hard to develop any PowerShell things on Windows. But there is PowerShell stuff on Linux, which makes it a little bit easier. But you'll still need to try and know how it interacts with the Windows system, even if you can't necessarily run it.
You also find a lot of old Windows, such as Windows 7, that doesn't really have, or like, didn't really work well with the Windows Defender, and it wasn't as aggressive as it is today.
Mm-hmm. Yeah, what else?
So I've noticed base 64 encoding is super common in these kind of fields.
Mm-hmm.
Is there any reason for that beyond just obfuscation? Making sure that if someone reading through the source code doesn't like read it?
Yeah, it takes in pretty much all kinds of information that you want, and then it outputs it in characters that almost anything can read.
More importantly, it takes in any binary data and will always result in an ASCII representable string.
Mm-hmm. Yeah.
Which most systems will, like, things can throw a fit when it's not ASCII, but almost everything will always allow ASCII in some form or another.
Gotcha.
Mind you, let me repeat it, it's ASCII representable with no spaces in it, too.
Yes.
Okay, gotcha. So it's for interoperability too.
Mm-hmm.
Yeah, it moves between systems nicely. It'll the same across all systems. You don't have to worry about like. I know I made some emoji challenges for 2 spooky CTFs ago.
Mm-hmm.
Yeah.
I had to have 2 different ones because you open it in one OS, it looks fine. It looks like a bunch of emojis. You open another, it's just a bunch of garbled text because it does not recognize specifics.
Huh.
Because UTF is questionable.
So and putting it in base 64 allows it to open as emojis on the.
It would allow me to take that raw data that would be there and
Right.
encode it in a manner that is going to remain the same across systems. That base 64 will
Right.
always encode the same data across systems, no
Rather
matter
than
the
you
data.
have, you just need two separate encoders based on the
Yeah.
system.
Yeah.
Cool. Thanks.
Oh, nice.
And so there's also a few other common ones. There's like base 32,
Yeah.
which I think would be all if you're in a if you're in an environment that removes case sensitivity, base 32 would be better because it is not. I think if I remember right, it's all uppercase and lowercase are not allowed,
Mm-hmm.
but most decoders and encoders treat it as case insensitive. So if you put in a lowercase value, it's not going to throw an error, it's just going to make it uppercase and then use it.
Cool.
Along with there's some other random benefits like base 58 and base something else. There's a few common standard base protocols like that are for encoding arbitrary data into a ASCII or relatively ASCII format.
Gotcha.
So here you can see an example of some real malicious PowerShell. First off, it's not easy to read. Even if it's not random characters, it's not easy to read. Any malicious PowerShell is going to use some strange PowerShell things to try and do PowerShell things. But normally it'll just have regularly named variables because you probably won't even be able to decipher what is going into that variable at first pass. It'll take a little bit to double check what everything does. You can see this one gets a bunch of information. Gets system info, ipconfig is all of the different interfaces that communicate with the network. Netstat shows all of the stuff that's communicating on the network itself. And you have different tasks, user, and then it double checks what the user is a part of and stuff like that. Gets some Outlook profiles, and then later on in this screenshot, we get some DLLs, and actually this isn't put together in order, but yeah. You can see some examples of what real PowerShell malware looks like. It gets strange. You can see this is a website. It might not look like it, but it is, trust me. That'll actually go somewhere. And then you can also use things like dotless IPs. There's lots and lots and lots of ways to try and obfuscate your malware, but most of the time Windows will be able to just parse it and look at it in normal ways. And then when you're actually trying to send this to different systems, there are many ways to get malware onto systems. One, you should be pretending that you are something that you're not. A lot of times it is images. It could also be screensavers have been really, really, really popular right now. If you get a screensaver file, it actually just acts like an executable, so you can execute whatever you want with it, and that's a common way for people to get your information. I know Linus Tech Tips is kind of the big one on that, but it happened to a lot of other people at the same time. But there's a lot to malware. I think it's super, super cool. It's pretty much like a puzzle every single time, and it teaches you to learn a lot about different languages and how they function. So yeah, I would say if you want to learn more of VX Underground, their website or Twitter, my website has some easier stuff, some stuff that I've done, and I'm going to put more stuff up on there later. But I think that's all I have for everyone today. I know it's a little bit of a short meeting, but I think that's okay. So yeah, thank you all for coming, and see you next week.